So here's a matrix 3 by 3. Let's say we're trying to find the eigenvalues and eigenvectors. What's our usual first step there? How do we start finding the eigenvalues? If ideally we want the matrix times some vector to equal a scalar times the same vector, how do we accomplish that? What would be a good first step? Yeah, how do we set up that characteristic polynomial? How would we write that out? If you're not sure, you can always go back to the definition. Everything about, if we subtract AV from both sides, and you can actually do it either way. I usually think of it as subtracting lambda v from both sides, but the important thing is we want to get everything to the same side. So if we subtract AV from both sides or subtract lambda v from both sides, we've got every term with a v on one side and just 0 on the other side. and yeah, we're ultimately trying to find all values of v that make this true. And we want values other than just the trivial solution, other than just 0. 0 technically works. 0 is an eigenvector, because if you fill in 0 vector, you get a times a 0 vector equals a scalar times a 0 vector. That is always true. But we're looking for the non-zero solutions because the fact that 0 is always a solution means it's not very interesting. It doesn't tell us anything useful about this matrix specifically. So if we want to solve for v, first of all, v shows up in both terms now, so we could factor that out. If you factor out v, what's left? What remains here if we factor a v out of both of these terms? We've got an a minus lambda, except for one slight problem. A is a matrix and lambda is a scalar. You can't actually subtract a matrix minus a scalar, but you can subtract a matrix minus a matrix. What's a matrix we could always fill in here as a multiplier that doesn't actually change anything? Yeah, if we fill in the identity matrix, lambda times I times v, we haven't actually changed the value, we've just changed how we're writing it. Now if we factor out v, we get a minus lambda I. And lambda I is a matrix, so this subtraction actually makes sense. You can subtract a matrix minus a matrix. And ultimately, this just means we're looking for a null space. We're trying to find the null space of the matrix a minus lambda I, because we're trying to find all vectors that turn into 0 when multiplied by a minus lambda I. That's effectively the definition of the null space. So we could say the eigenvectors are the null space of a minus lambda I. But we still need to figure out what lambda is, because we know A, the matrix, but we don't know what value lambda is. But again, we want to make sure we get more than just the trivial solution. We want more than just v equals 0. And what has to be true about a matrix for its null space to be more than just the 0 vector, to get more solutions than just v equals 0? Or to put it another way, if we go off to the side here and say, let's just call this matrix M for now. If we've got M times V equals 0, what's one way to solve that for V? Is there any way you could just get rid of M here? Yeah, if we left multiply both sides by M inverse, that's doing the same operation to both sides. Now on the left side, M inverse times N is the identity matrix, so that effectively cancels out. And we'd be left with just V equals, and then any matrix times a zero vector is just a zero vector. So that means we end up with V equals 0 as the only solution, unless what? What has to be true about M for this not to result in 0 as the only solution? Is there any property M could have such that we can't end up with just 0 as the only solution? That we can't do this step? Yeah, M has to be non-invertible. So we want M to be singular, that is non-invertible. So we can avoid this. We don't want 0 to be the only solution. The only way we can avoid 0 being the only solution is by this matrix being non-invertible. And of course, that matrix isn't actually N here. That matrix is the A minus lambda I. So really the idea of finding the eigenvalues is we want a lambda that will make A minus lambda I non-invertible, because that's the only way we can guarantee more eigenvectors than just a zero vector. Any questions on the theory behind that so far? And what's generally the fastest way of making sure a matrix is non-invertible or checking whether it's invertible or not? Yeah, we want the determinant to be 0. We want the determinant to equal 0. That's really the key to the whole thing. The key to finding eigenvalues is we want lambda values that make A minus lambda I have 0 as the determinant. So we can actually start with that. We can, from the original matrix, if we want to find the eigenvalues, you don't necessarily have to go through this whole procedure every time. We can just say, we want to assume that the determinant of A minus lambda I equals 0. And this comes from all these steps, starting with the definition. Everything about eigenvectors and eigenvalues always starts from the definition. But we don't have to go through these steps every time. We can just say, to find the eigenvalues, we can start by saying determinant of A minus lambda I equals 0. By setting that equal to 0, we can solve for the lambda values that make this work. And those lambdas are the eigenvalues. Any questions on that setup so far? So let's write this out and see if we can run the calculations. Minus lambda I just means we're subtracting lambda from which values in the matrix. Like, what is lambda I actually going to look like? It's going to be a whole bunch of zeros, except what values are non-zero in that. Yeah, the diagonal matrix, because the identity matrix is just ones on the main diagonal, zeros everywhere else. If we multiply by lambda, all those ones on the main diagonal turn into lambdas, and then we've got zeros everywhere else. By the way, if you see a matrix written like this with some of the entries filled in and the rest blank, the implication there is that the blank values are all zeros. I usually go ahead and actually write those in just for clarity. But if you see blank spaces in a matrix, that usually means those blank spaces are meant to be zeros. So subtracting lambda I really just means subtracting lambda from everything on the main diagonal. 5 minus lambda, 2 minus lambda, negative 3 minus lambda, and keeping everything else the same. So let's write that out. A minus lambda I. So we keep all these values, but we subtract lambda from everything on the main diagonal. and we want to take the determinant of that, often just written as vertical bars instead of brackets, and set that determinant equal to 0. And how would we actually evaluate a 3x3 determinant? What's one way of accomplishing that? Yeah, the idea of cofactors. We can take the cofactors, that is all the values from one row or one column, and use those as coefficients multiplied by smaller determinants or subdeterminants. So if we take, and we could take any row or column. Typically, if there's a row or column that has lots of zeros in it, I would recommend using that because the zeros make the numbers easier to work with. But we could use any row or column. Let's say, for instance, we use the first row as our cofactors in the sense that we're using those values as coefficients. So 5 minus lambda, 3, and -6. And the idea is each one of those is going to be multiplied by a smaller determinant, often called a subdeterminant. But we're also going to be alternating alternating adding and subtracting, alternating plus and minus. Typically, if you're dealing with an odd numbered row or column, like in this case, this is the first row, so that's an odd numbered row, you start with plus. If we were dealing with an even numbered row or column, like the second row or the second column, or in a larger matrix, maybe the fourth column, you'd start with minus and then alternate minus, plus, minus, plus. But for an odd numbered row or column, start with plus and then alternate. And then for the subdeterminants, the smaller 2x2 determinants, what you would do is that entry we're looking at, 5 minus lambda, the cofactor, ignore everything in that row and ignore everything in that column. And what's left will be a smaller, in this case, 2x2 subdeterminant. So 5 minus lambda, ignore that entire top row, ignore that entire left column. We're left with just these 4 numbers. 2 minus lambda, 2, 3, -3 minus lambda. Then for the 3, that's in the top row middle column. So ignore the top row, ignore the middle column. We're left with -2, 2, 2, -3 minus lambda. And likewise for the -6, that's in the top row right column. So ignore the top row, ignore the right column, and we're left with another 2x2 subdeterminant. -2, 2 minus lambda, 2, 3. So this would be the cofactor expansion in the sense that we use a single row, all the values in a single row as cofactors, they're coefficients here. And each one of those is multiplied by the subdeterminant of everything not in that row and column, and then alternate adding and subtracting. That's a very useful way to define the determinant and evaluate what it's going to be. And of course, we still want that to equal 0. Any questions on that expansion so far? And then each of these 2x2s you could also think of as a cofactor expansion. Let's say we take the top row, this thing times the determinant of everything not in that row and column, which is just a single number, minus this thing times everything not in that row and column, which is just a single number. Note that this works out to the same, the usual multiply the diagonals and subtract. This times this minus this times this. So you get the same result anyway. So for the 2x2, we can use that shortcut, multiply the diagonals and subtract. So 2 minus lambda times -3 minus lambda minus 2 times 3. And that whole thing multiplied by 5 minus lambda. Minus 3 times -2 times -3 minus lambda. I'm going to go ahead and multiply that out. We get +6 plus 2 lambda minus the other diagonal, minus 2 times 2. Plus -6, so that's -6 times this diagonal, -2 times 3, minus this diagonal, minus 2 times 2, minus 2 times negative lambda. Any questions on that so far? The 2x2 determinants. And then the rest is just simplifying. We multiply, for instance, 2 minus lambda times negative 3 minus lambda, we get negative 6 plus 3 lambda minus 2 lambda is just plus lambda. Minus lambda times minus lambda is plus lambda squared. Minus 6, so that combines with the negative 6 already there and becomes negative 12. And that whole quadratic is multiplied by 5 minus lambda. Minus 3 times each of these. And note that the 6 and the negative 4 become just 2, times negative 3 is minus 6. Negative 3 times 2 lambda is minus 6 lambda. And then this negative 6, again, we could combine these. Negative 6 minus 4 is negative 10. Minus 2 lambda becomes plus 2 lambda. Those get multiplied by negative 6. So negative 6 times negative 10 is plus 60. Negative 6 times 2 lambda is minus 12 lambda. Yeah. And then this, we would just distribute the 5 to each of these terms and distribute the negative lambda to each of these terms. So 5 times negative 12, 5 times lambda, 5 times lambda squared, negative lambda times negative 12, negative lambda times lambda, minus lambda squared. And negative lambda times lambda squared, negative lambda cubed. And that combines with all this stuff. Any questions on that expansion so far? So let's combine like terms, and we back up to here for a moment. Let's combine like terms and see what we get. We've got a single negative lambda cubed. If we take a look for all of the lambda squared terms, we've got a negative lambda squared and a 5 lambda squared. And I think that's it. Negative lambda squared plus 5 lambda squared is 4 lambda squared. Then if we take a look for all of the lambda terms, we got 12 lambda plus 5 lambda. That's 17 lambda. But you got 12 lambda and minus 12 lambda. Those just cancel out. 5 lambda minus 6 lambda is just minus lambda. And then if we take a look at all of the constants, we've got negative 60, minus 6, plus 60. 60 and minus 60 cancel out, so we just get minus 6. So it looks like that's the entire characteristic cubic. Any questions on the math behind that so far? And I usually find it easier to deal with polynomials if the first coefficient is positive. Doesn't have to be, but let's just multiply this by -1. So we get lambda cubed minus 4 lambda squared plus lambda plus 6 equals 0. So we would call this the characteristic polynomial, or in this case, the characteristic cubic, because it is specifically a cubic function. So if we can solve that, we'll get the eigenvalues. Any questions on finding that characteristic cubic so far? And since it's a cubic, how many solutions, or at least at most, how many solutions can you expect from a cubic? Yeah, we can expect at most 3 solutions. Because if you've got a cubic, we would typically expect the shape to be this at its most complicated. That could cross the lambda axis up to 3 times. So we can expect as many as 3 real solutions. It's also possible, let's say this is higher up, maybe you get a cubic like this. In this case, how many real solutions would we get? Yeah, it only crosses the axis once, so there would be one real solution. There would also be two complex solutions that are complex conjugates of each other. So it's possible for a matrix to have complex eigenvalues. Other possibilities would include if you've got going through the axis and then coming down and hitting it with a minimum or maximum, but then bouncing back up. In that case, you get two real solutions. One of them would act as a repeated root, like that would show up in the factored form twice. Or it's also possible that maybe there's an inflection point on the axis. In that case, you just have one real solution that's a repeated solution. Like your factored form would be lambda minus something cubed. So these are all possibilities. You might get three real solutions. You might get one real solution and two complex solutions. You might get two real solutions and one of them's repeated. You might get only one real solution and it's repeated 3 times. But you will expect at most 3 eigenvalues. So let's see if we can find those eigenvalues. That means we're going to need to find some way of solving a cubic. And if there's no obvious way to factor it, there isn't really a cubic formula like there is a quadratic formula. There is a procedure, an algorithm for solving every cubic guaranteed. So kind of like the quadratic formula, but it's a multi-step process. That gets very complicated and often ends up involving complex numbers, even if the solutions are all real. So I've never actually seen that taught in any class. And it doesn't really seem all that applicable. But there is a technique called the rational roots theorem that's often very useful. The idea is if we can find a solution of this, like if we find that some specific value is a solution, we can factor out lambda minus that value and see what's left. So as soon as we find a solution, we can continue from there. But if we just try guessing and checking, there's infinitely many lambda values to try out. So we don't want to waste time trying infinitely many values. But we can use a very clever idea called the rational roots theorem. The rational roots theorem applies to any polynomial, at least any polynomial where you can write the coefficients as whole numbers. The idea is if you've got a polynomial of any degree whose coefficients are whole numbers, if that polynomial has any rational roots, and it might have roots that are rational, maybe they're all rational, maybe they're all irrational, maybe some rational, some irrational. But if this has any rational roots, if a polynomial, let's say a times lambda to the n being the degree, so the highest power of lambda, plus a bunch of other stuff, ending with some constant plus z. If you've got a polynomial a times lambda to the highest power plus a bunch of other powers plus a constant z, if this has any rational roots, rational just means it can be written as a fraction of whole numbers. So we can write it as a fraction. They must be of the form a fraction. And the numerator and denominator of that fraction have to be very specific formats. The numerator is going to have to be a factor of z. That is a factor of that final constant being added. And the denominator has to be a factor of a. That is the coefficient on the highest power of lambda. And they could be positive or negative. But this drastically narrows down the list of possible solutions. You're narrowing this down from there's infinitely many lambda values to check in our guess and check procedure to only a few, the possible fractions of factors of z and a. So this narrows down the list of values we have to check. Any questions on that so far? Then let's try this out. In this case, z is 6, that is the constant being added, and a is just 1, because we just got 1 lambda cubed. So that means the solutions we're looking for are factors of 6 over factors of 1. With a plus or minus as well. What are the factors of 6? That is, what whole numbers go into 6 evenly? Yeah, 1, 2, 3, and 6. So we can, those are the only numbers we can use as numerators if we want a rational solution. And factors of 1, that's just 1. And of course, we had the plus or minus as well. So if you had more than just 1 as a factor, you'd want to look at every single possible combination of numerator and denominator. In this case, the only denominator is 1. So we just got 1 over 1, 2 over 1, 3 over 1, 6 over 1. So the possible lambda values are 1 over 1, 2 over 1, 3 over 1, 6 over 1, and also the negatives of those as well. -1, -2, -3, -6. And of course, there might also be irrational lambda values. But if there are any rational solutions, they have to be from this list. So we've narrowed it down from infinitely many lambda values we have to guess and check to only 8 values we have to try out. If there are any rational values, they will be on this list. So this is a very useful way of narrowing down the possible things to try out. Any questions on that listing so far, the rational roots theorem?
I had a quick question.
Yeah, go ahead.
Does the rational roots theorem also apply to like quadratic equations, or does it have to be higher than that?
Yes, any degree of polynomial. So you can use this if you see a quadratic that you think is probably factorable, but you're not really sure how it factors. This can be a useful way of narrowing down the possibilities. And then just try all of those numbers as roots and see if any of them work.
Thank you.
And again, this only applies to rational roots. If the polynomial has any irrational solutions, they will not be on this list, of course. This only lists out the possible values for rational roots. And it might be the case in which that there's no rational roots at all. Maybe all the solutions are irrational, in which case this is no help at all, other than telling you they're all irrational. None of the rational values work. But if it has any rational values, this will find them. So let's try that out. We've got the possible rational lambda values. We can check those just by plugging them into the polynomial. So let's try that out. We can just check these one at a time, usually starting from the ones that are easiest to run the calculations on. Like for instance, let's fill in 1. If we try 1, we get 1 cubed minus 4 times 1 squared plus 1 plus 6. That's 1 minus 4 plus 1 plus 6. 6, 7, 8 minus 4 is 4. So that is not 0. So that means positive 1 doesn't work. We can cross that off the list. What do you want to try next? Now that we know 1 doesn't work. I guess we may as well just go in order. Let's try 2. If we try 2, lambda equals 2 maybe. We get, if we just fill in 2 for every lambda, 2 cubed minus 4 times 2 squared plus 2 plus 6. 2 cubed is 8 minus 4 times 2 squared is 4 plus 2 plus 6. So that's 8 minus 16 plus 2 and 6 is 8. 8 and 8 make 16, minus 16 is 0. So what does that tell us? Yeah, 2 really is a solution. Lambda equals 2 is an eigenvalue because it's a solution, a root of this characteristic quadratic or characteristic cubic. So we know lambda equals 2 is an eigenvalue. And what we can do with that, we can just leave that and we can continue checking these values. But sometimes a more useful way is, now that we know lambda equals 2 is a root, if 2 is a root, then lambda minus 2 should be a factor. Which means we should be able to factor a lambda minus 2 out of this whole thing. And if you factor a lambda minus 2 out of a cubic, what kind of function will be remaining? What happens if you take a cubic and divide by a first degree binomial like this? We should be left with a quadratic, exactly. And then we can factor that quadratic or use quadratic formula, whatever works out. So let's try that. Let's take this, this cubic and divide by lambda minus 2. One way to do this would be to use polynomial long division. That is, ask yourself how many lambda goes into lambda cubed, subtract that, figure out what's left over, then how many lambda go into whatever lambda squared is left. But I find often a much more useful way of writing this is to think of this as an area of a rectangle. We've got some rectangle. We want the area to be this result. But we want to split that out into lambda minus 2 times something. So if you think of that area as height times width, let's say the height is lambda minus 2. So if you think of this distance as lambda and this distance as -2, and a distance being -2 doesn't geometrically make sense, but the algebra still works out. So lambda and -2 multiplied by some unknown quadratic, something lambda squared plus something something lambda squared plus something lambda plus something. And we want those to add up to lambda cubed minus 4 lambda squared plus lambda plus 6. We're going to have something lambda squared here, but specifically how many lambda squared times lambda equals lambda cubed. If we put a something lambda squared here, what does that coefficient have to be? If we want these to multiply to exactly lambda cubed? Yeah, just 1. So we'll have 1 lambda squared here, plus something lambda plus something. If we actually distribute this, the lambda squared gets multiplied by both of these. Lambda squared times lambda is lambda cubed. Lambda squared times -2 is -2 lambda squared. But we don't want -2 lambda squared, we want -4 lambda squared. So how much more lambda squared do we need here? If we want both of these lambda squared terms to add up to -4 lambda squared. Yeah, we need another -2 lambda squared so that these add up to the correct amount. And -2 lambda squared can be achieved by multiplying lambda by what? Yeah, that's also going to have to be a -2. -2 lambda times lambda is what you'd have to multiply to get -2 lambda squared. But of course, that -2 lambda also needs to get multiplied by this -2. -2 lambda times -2 becomes +4 lambda. But we don't want +4 lambda, we want +1 lambda. So what more do we need here so that 4 lambda plus this equals exactly 1 lambda? What would you have to add to 4 lambda to turn it into 1 lambda? Yeah, it should be -3 lambda. And to get lambda times something equal -3 lambda, this is going to have to be -3. And that -3, of course, also multiplies by this -2 to get this area. -3 times -2 would be +6, which matches up to the +6 we have at the end. So that verifies that this really does go into the cubic evenly with no remainder. So it really is a root, or this lambda minus 2 really is a factor. So this tells us that the characteristic cubic can be factored into lambda minus 2 times lambda squared minus 2 lambda minus 3. So let's write that out. We can now say with certainty that our characteristic cubic can be written as lambda minus 2 corresponding to the root we've already got, times lambda squared minus 2 lambda minus 3. And now what's left is just a quadratic. So we could either repeat the rational roots theorem with this more limited value, so we have an even smaller list of values to try out, or we might be able to just factor this. Do you see an easy way to factor lambda squared minus 2 lambda minus 3? Does that factor nicely? We want values that multiply to lambda squared, so lambda times lambda. Do we have some values that multiply to -3 but add up to -2? Yeah, lambda minus 3 times lambda plus 1 should do it, because that way -3 lambda plus 1 lambda adds up to -2 lambda, but -3 times 1 is -3. So this would be factored form. Lambda minus 2 times lambda minus 3 times lambda plus 1 equals 0. So our solutions then, the roots of the original characteristic cubic will be -1, +2, which we already have, and +3. So those will be the 3 eigenvalues of that original matrix. Any questions on that so far? So let's write that out. And for simplicity, since we've got eigenvalues -1, 2, and 3, I'm going to call those lambda 1, lambda 2, lambda 3. So our eigenvalues are lambda 1 is -1, lambda 2 equals 2, lambda 3 equals 3. And the order doesn't really matter. You can label these in any order you want, as long as you're consistent about it. I just usually find it kind of confusing if I call -1 equal to lambda 3, or 2 equal to lambda 1, or something like that. So choose values that are going to be easy to remember and not easy to mix up. So we've got the 3 eigenvalues of the original matrix. Any questions on the process for finding those eigenvalues? All right, then let's use those eigenvalues to find the eigenvectors. And for the eigenvectors, if we take a look back at the process we used to get the characteristic quadratic in the first place, we started with AV equals lambda V. We subtracted lambda V from both sides. We factored out V. We're left with A minus lambda I times V equals 0. This was the last step where we actually solved V. After this, we kind of abandoned V and focused on just the matrix A minus lambda I and the properties it had to have. But if we backtrack to this, the last time we saw V, we can now think of this, now that we know lambda, we can think of this as just solving for V. That is, finding the null space of A minus lambda I. And how would you typically solve for V? How do you usually find the null space of a matrix? Well, that's what we have here. We've got a matrix times V equals 0. From that, how do you actually find the null space? Like, what calculations would you have to actually do with the matrix to find the vectors that become 0 when multiplied by the matrix, if you want to solve something times V equals 0? What process or what calculation would you typically do there? Because keep in mind, we can actually fill this in. Let's say we fill in -1 for lambda. If we subtract -1 from everything on the main diagonal, because lambda I just means lambda's on the main diagonal. So if we just subtract -1 from everything on the main diagonal, 5 minus -1, 2 minus -1, -3 minus -1, and then everything else unchanged. we're trying to find, yeah, we can row reduce, right? If we're trying to find this matrix times some unknown vector equals 0, you can just augment this matrix with a 0 vector and row reduce. The usual method we use for solving a matrix equation. In general, if you're trying to solve mx equals b, augment m and b vector, and then row reduce. In this case, the final column is all zeros. Those zeros are not going to change. So we don't really even need to keep track of those zeros. Just keep in mind there's an invisible column of zeros here we can fill in at the end. So can we row reduce this? Or what could we do to row reduce? Do you see any simplifications we could make, or any way we could make these numbers easier to work with or cancel something out? One thing I'm noticing right away, what do you see about all the numbers in the first row? Six, 3, -6, those are all divisible by 3. So let's go ahead and multiply that first row by 1/3 just to make the numbers easier to work with. That gives us 2, 1, -2. And I think that's going to make the first column a lot easier to deal with. Because if we think of this top left number as a pivot, the first non-zero in the row, how could we use that pivot to eliminate everything else in that column? What row operations would work here? For instance, we could modify the second row by adding what? Yeah, if we just add the first row exactly as is. Whereas for the third row, what would we have to add? Yeah, subtract row 1, or you could think of that as adding the opposite of row 1, or adding -1 times row 1. And let's see what we get. First row stays the same. Second row, -2 plus 2, 3 plus 1, 2 plus -2. Third row, 2 plus 2 minus 2, 3 minus 1, -2 minus -2, cancels out. And then these rows we could simplify by, in this case, for instance, multiplying this row by 1/4. And multiplying this row by 1/2. That turns those into 1s, which is going to make things a lot easier. So we get 2, 1, -2, 0, 1, 0, and another copy of 0, 1, 0. And that's really useful. We now have a duplicated row. So what's going to happen in our next row reduction step? Or what could we do with that pivot? Now that we've got the first pivot alone in its column, and the next row has a pivot right here, what could we do with that pivot for our next elimination steps? Yeah, we subtract row 2 from row 3. And also we want reduced row echelon form. So we want to cancel out everything above the pivot also. So let's subtract row 2 from row 1 as well. We'll cancel out this 1. So top row just becomes 2, 0, -2, because the 1 cancels out and these zeros don't do anything. Second row, we're not changing. And what's the new third row? Yeah, all zeros, which is good actually, because typically when you're solving a system of equations, what does it mean if one of the rows comes out to all zeros? If one of the rows completely cancels out, what does that tell you about the solution? First of all, it tells us the matrix is non-invertible, which is good. We were deliberately designing this matrix to be non-invertible by setting its determinant equal to 0. And what does it tell you about the original system of equations? Yes, and the determinant is 0, which is also how we set this up. Also, if one of the rows becomes all zeros, how many solutions do you expect? If we treat this as solving a system of equations. If this were able to reduce all the way to the identity matrix, we get just one solution. But if it can't reduce to the identity matrix, if one of the rows turns into all zeros, what does that suggest about the number of solutions? If we were to write these out as equations again, like let's say we call our eigenvector v1, let's just say those values in it are a, b, and c. If you write out this third row as an equation, we got 0a plus 0b plus 0c. And then there's also the final column of zeros that we've been ignoring, but it's still there. We just haven't been writing it out. Equals 0. What values of a, b, and c would make this equation true? If we know that 0a plus 0b plus 0c equals 0, does that give us any restrictions? Or what could a, b, and c equal there? Well, that's a different row. So ignoring that row for now, if we look at just the third row, you could have a, b, and c be all 0, but that's not the only solution. Yeah, they could be anything. If like a is 1,000, b is -2, and c is 5 square root of pi. 0 times 1,000 plus 0 times -2 plus 0 times 5 square root of pi is 0. According to this third row, if you have a row of all zeros, that row is saying, I don't care what a, b, and c are. A, b, and c could be any values, and they still make this row true. So a row of all zeros tells you that row provides no extra restrictions. That doesn't always mean you have infinitely many solutions, but it at least means that this row does not provide any restrictions, and we now only have 2 rows of restrictions. Effectively, we now have a system of 2 equations, 3 unknowns, so we should expect it at least could have infinitely many solutions. And that's what we want. The whole point of setting up determinant equals 0 to make the matrix non-invertible is so that we get many solutions instead of just the trivial solution. We want infinitely many eigenvectors here. And that's exactly what we're going to get. One more simplification we can make here. Everything in the first row is multiples of 2. In fact, they're all just 2 and -2. So I'm going to multiply that by 1/2. Make the resulting numbers easier to work with. So that becomes 1, 0, -1, 0, 1, 0. And I'm not even going to bother writing in the row of all zeros because it does not provide any extra information. It's still there, but it doesn't provide us any information. But generally, we should expect that. Anytime you're solving for eigenvalues by row reducing, you should expect at least one of the rows, possibly more, to cancel out to all zeros. If none of them do, something has gone wrong. So that's something to watch for. We should expect infinitely many eigenvectors, so we should expect at least one row to zero out. So rewriting these rows as equations. Again, we're assuming that the eigenvector is 3 by 1. So let's just say v1 is a, b, c. What would the first row look like as an equation in terms of a, b, and c? If we think of these as coefficient of a, coefficient of b, coefficient of c, what would this row look like as an equation? Yeah, 1a plus 0b plus -1c, that is a minus c, equals 0, with the 0 being from that invisible column of zeros we've been ignoring. And then what does the second row look like as an equation? again, if you think of these as coefficients of A, B, and C, what would that row turn into? Yeah, B equals 0, because we've got 0A plus 1B plus 0C equals 0. So this tells us B has to equal 0. We can fill that in right now. B must equal 0. And what does it tell us about A and C? If you solve this for one of those variables, like let's say you isolate A here, what would you get? Yeah, they've got to be the same. Add C to both sides, you get A equals C. So we can think, let's say we treat A as a fixed variable and C as the free variable. We're saying C could be anything, but A has to equal C. So everywhere we've got A, we can replace it with C. Everywhere we've got C already, we'll just leave it as it is with the implication that C could be anything. And if we factor out C, what's left? Yeah, 1, 0, 1. That then is an eigenvector. And note that since C could be anything, any scalar multiple of 1, 0, 1 will also be an eigenvector. So we could say, let's C equal 100, 100, 0, 100. Or we could say, let C equal negative 3.7. So negative 3.7, 0, negative 3.7. These would all be eigenvectors with eigenvalue negative 1. Of course, we only need to list out one of those, probably the simplest one, 1, 0, 1. And the implication, which we don't need to bother writing usually, but the implication is that any multiple of that will also count. So that's one of the eigenvectors. The eigenvector associated with negative 1 is 1, 0, 1, and any multiple of them. So we would typically call that V1. V1 is the vector 1, 0, 1. And by the way, how could we check that to verify that this really is an eigenvector? Now that we've got an eigenvalue and eigenvector, how do we verify that that really is the eigenvector associated with that eigenvalue? What's the definition of eigenvectors and eigenvalues in the first place? Yeah, we can always go back to that definition, AV equals lambda V. So if we want to check, is this really an eigenvector? Did we actually calculate this right? We can always go back to AV, check, is it equal to lambda V? So if we try that out here, we've got our A matrix. Multiplied by the eigenvector 1, 0, 1. So if we multiply that out, row and column, then we would get 5 plus 3 minus 6. 5 plus 3 minus 6 is negative 1. Negative 2 plus nothing plus 2 is 0. 2 plus nothing plus negative 3 is negative 1. And note that A times V equals exactly negative 1 times V, same result. So this is one of the really nice things about eigenvectors and eigenvalues. It takes a lot of work to get there, but once you've got it, you can always check your solution immediately by going back to the definition. Multiply the original matrix times your alleged eigenvector, and multiply the eigenvalue times the eigenvector, and check to make sure they give you the same result. Oh, and how is B equal to 0? If you go back to the second row of the row reduced echelon form, our second row was 0, 1, 0. And then the 0 in the final column of zeros we weren't writing out. If you write this row as an equation, again, if you think of these as coefficients of A, B, and C, we've got 0A plus 1B plus 0C equals 0. 0A and 0C are just 0, so we're left with just 1B equals 0. So that second row tells us B has to be 0, no other way around it. A and C could be anything as long as they're the same, but this row says that B has to be 0. So 1, 0, 1, or any scalar multiple of that will be the eigenvector. Or really the eigenspace. Since it's a collection of infinitely many eigenvectors that form a vector space, we would say the eigenspace is all multiples of 1, 0, 1. But we would usually just describe that as the eigenvector is 1, 0, 1, with the implication that that's the basis for an entire eigenspace. So any multiple of that will also work. Any other questions on that so far? Then let's see if we can find the other eigenvectors. Same procedure, we would just use the other eigenvalues. So for instance, let's say we fill in lambda equals 2. Again, we'd write out the A matrix, but we'd be subtracting this eigenvalue from everything on the main diagonal because we're looking for A minus lambda I. So 5 minus 2, 2 minus 2, negative 3 minus 2, and then keep everything else the same. Again, we're formally augmenting with this with a column of zeros, but we can ignore that column of zeros because it's never going to change. And then to row reduce this, once again, take a look for any rows that are all multiples of a single easy value. For instance, top row, we could divide by 3. So let's start with that. 3 over 3, 3 over 3, negative 6 over 3. And also, although it's kind of breaking the usual algorithm, I'm noticing that this negative 2 could really easily cancel out this 2. So we might want to do that in the same step. It's not part of the standard Gauss-Jordan elimination procedure, but there's a lot of flexibility here. There are many ways to row reduce a matrix. As long as you get to the row reduced echelon form, it'll get the same result. So let me go ahead and make this easier on ourselves by adding row 2 to row 3 in this first step. Oh, also this first row, the second row is all multiples of 2. So let's multiply that by 1/2 as well. So it becomes negative 1, 0, 1. And then the third row is now 2 minus 2, 3 plus 0, negative 5 plus 2. Any thoughts on how we could proceed from there? And again, there's a lot of different ways to do this. You could just follow the step-by-step Gauss-Jordan algorithm, or you could start looking for shortcuts. What do you think would be a good next step here? Do you notice anything interesting about this row? Or what could we do with this row to make it easier to work with? Yeah, let's divide that whole row by 3. Multiplied by 1/3. And also another thing I'm seeing here, again, this is kind of going against the strict algorithm, but I'm noticing this row has a pivot in the first spot, and this 0 here and this 1 here will probably make things easier as well. This one is going to have a pivot in the second spot, which is going to be 1 as soon as we divide by 3. So we might want to shuffle these rows around. I think it might be easier if we put this second row in the top spot and this third row in the middle spot. So let's shuffle these around. In fact, let's multiply this row by -1 to turn the first number, the pivot, into a +1, and shuffle it up to the top, because we are free to rearrange rows. The order of the rows doesn't really matter. Let's shuffle the third row up to the second spot and the first row down to the bottom. Just because I've got a hunch that this is going to make it easier to work with the resulting numbers. So the original first row becomes the bottom row. -1, 0, 1 times -1, and we're shuffling that up to the top. So that becomes 1, 0, -1. And the third row, we're multiplying by 1/3. So that just becomes 0, 1, -1, which we're bumping up to the middle row. We haven't lost any information. We're just rearranging the information we already have. And I'm thinking this is going to be useful because now we can use this pivot to eliminate the one thing under it and use this pivot to eliminate the one other thing in the row. So let's go ahead and do that. I think that'll finish up the row reduction. If we take the third row and subtract the first row and also subtract the second row, all in one step, I think this is going to make the results a lot easier to work with. So first row, we're keeping the same. Second row, we're keeping the same. Third row, we're subtracting everything in the first and second rows. So 1 minus 0 minus 1, 0. 1 minus 1 minus 0, 0. -2 minus -1 minus -1 again, also 0. Which again, we should expect. We should expect at least one of the rows to become all zeros because we're looking for infinitely many solutions. So that's our reduced row echelon form. There are many ways to get here. This is just one procedure using some clever shortcuts, but any process will eventually get here if you're seeking reduced row echelon form. Many ways to get there, but they all lead to the same result. That's really the whole point of reduced row echelon form. It's unique. Anyone starting with the same matrix and going through any procedure they want will eventually get to the same reduced row echelon form. And again, let's say we're treating the eigenvector as, let's just call this ABC again. Our equations, A plus nothing minus C equals 0, and nothing plus B minus C equals 0. And then third row is just going to be 0 equals 0. That's always true, so it doesn't provide any extra restrictions. These are the only restrictions on the values of A, B, and C. The first row tells us A can be replaced by what? If we solve this for A, what would we get? And if we solve the second equation for B, what would we get? Yeah, A equals C, and likewise B equals C. And we're treating C as a free variable because we're defining everything else in terms of C. So we're saying C could be anything, we'll just leave it as C, but A has to equal C and B has to equal C. Factor C out of that, and then what's left? Yeah, 1, 1, 1. So that would be the eigenvector associated with lambda equals 2. So we'd say V2 equals 1, 1, 1. And again, any scalar multiple of that will also work. So 327, 327, 327, or -5 pi, -5 pi, -5 pi. Those would also be eigenvectors associated with lambda 2 equals 2. And again, you could check that by multiplying the matrix times this vector. You should get exactly 2 times this vector. That is 2, 2, 2. So try that on your own just to verify, but that should be the result. And then V3, we go through the same procedure. We're running kind of short on time, so I'm going to skip this one, but you go through the same process. Subtract the eigenvalue 3 from everything on the main diagonal, and row reduce, and see what you get. And let me double check what I actually got there. It was I think that was 0, 2, 1. I think so, yeah. Yeah, that checks out. So this would be the third eigenvector. And again, you find that using the same process, subtract lambda I, specifically subtract 3 from everything in the main diagonal, row reduce, turn it into equations, and it should work out to this. So try that on your own to get some more practice. But I want to skip that for now so we can move on to what else we can do with these eigenvalues and eigenvectors. Now that we've got the eigenvalues and eigenvectors, there are many applications of this one application that someone was asking about earlier is diagonalization. Diagonalization is an idea where we rewrite the original matrix in terms of a purely diagonal matrix. That is, values that are not zero, possibly on the main diagonal, but definitely zeros everywhere else. The idea is we're going to rewrite matrix A as a purely diagonal matrix. That is, let's say D1, D2, D3, and then zeros everywhere else. And these values on the diagonal could also be zero. The only thing diagonal means is that everything not on the main diagonal must be zero. So we're rewriting matrix A as the purely diagonal matrix, flanked on both sides by some other matrix and the inverse of that other matrix. So that's the main idea here. We want a we want the diagonal matrix flanked by a matrix on the left and the inverse of that matrix on the right side. And it turns out that the matrices that will work here, the diagonal matrix we need is just the eigenvalues. So it turns out these values are just lambda 1, lambda 2, lambda 3. And then this M matrix is a matrix whose columns are the corresponding eigenvectors. So V1, V2, V3 as the columns of the matrix. And then M inverse is just that matrix inverted. The reason why this works is if you multiply M times D, you're multiplying each one of these columns by the corresponding single scalar. So you get lambda 1, V1, lambda 2, V2, lambda 3, V3. And if we rearrange this by multiplying both sides by M, the M and M inverse cancel out, so you get A times M on the other side. A times M is A times the matrix consisting of eigenvectors. Multiply that out, you get A times V1, A times V2, A times V3. And the whole point of an eigenvector is that A times V1 equals lambda 1 times V1. And A times V2 equals lambda 2 times V2. And A times V3 equals lambda 3 times V3. So A times the matrix whose columns are eigenvectors gives you the same result as that matrix whose columns are eigenvectors times the diagonal matrix whose diagonal entries are the eigenvalues. So this is one way to write it. This is essentially the definition of eigenvectors, but with all the eigenvectors combined into a matrix rather than as single columns. And if you right multiply both sides by M inverse, you get back to this diagonalization idea. So that's the core concept of diagonalization, that if you write out a matrix whose columns are the eigenvectors, and write out a diagonal matrix whose diagonal entries are the eigenvalues in the same order, like this eigenvalue corresponds to this eigenvector, and this eigenvalue corresponds to this eigenvector, and so on, then that should work as a diagonalization of the original matrix. So in this case, we can write this as M would be the eigenvectors as columns. So 1, 0, 1 is a column, 1, 1, 1 is a column, 0, 2, 1 is a column. This would be our matrix here. And then the diagonal matrix would use the eigenvalues as the diagonal entries. So eigenvalue -1, eigenvalue 2, eigenvalue 3, and then zeros everywhere else. And then we would just need to invert this matrix. And how do you invert a matrix? Or what's one way of writing out the inverse of the matrix? If you wanted to find the inverse of a matrix, the usual procedure for that is you just take that matrix augment with the identity matrix and row reduce all the way to reduce row echelon form. Yeah, exactly. Augment with the identity, row reduce. The left side ideally should turn all the way into the identity matrix. If it doesn't, then M is not invertible. But this should be invertible as long as you have as many different eigenvectors, as many linearly independent eigenvectors as the width of the matrix. And then when you reduce that to the identity matrix, the right side will turn into M inverse. So that's one way to do it. Augment with the identity matrix, row reduce. Proving if a matrix is diagonalizable, as long as it has as many linearly independent eigenvectors as the width of the matrix. Like in this case, this matrix has 3 columns. It also has 3 linearly independent eigenvectors. So that should be enough. If it only had 2 linearly independent eigenvectors, then if we just had like one eigenvector and a second eigenvector and I don't know, maybe a copy of one of the eigenvectors we already have, those wouldn't be linearly independent columns. So that matrix would not be invertible and M inverse would not exist. So diagonalization only works if this M matrix is invertible. And that's only the case. That's the case if and only if it has enough eigenvectors, linearly independent eigenvectors, to fill up all the columns. And typically you would only get repeated eigenvectors, like not enough linearly independent eigenvectors, if the characteristic quadratic has a repeated root. And even then, it's not guaranteed. You might have a repeated root in the characteristic quadratic or cubic or whatever, but still have n independent eigenvectors. The only way to tell is to actually find the eigenvectors and check, do you have as many independent eigenvectors as the number of columns in the original matrix? If you do, then the matrix is diagonalizable. Any other questions on diagonalization? And again, this is really easy to check. Well, not necessarily easy. It's very straightforward to check your answer. It's just a little tedious. Once you diagonalize it, M, D, M inverse, actually finding M inverse, you can multiply that out. Multiply M times D, multiply that whole thing times M inverse, and verify that you really get back to the original matrix. If so, then you got it right. And one of the really useful applications of diagonalization is raising a matrix to a power. Like, let's say you wanted to raise matrix A to the 5th power. Multiplying A times A times A times A times A is going to be really tedious. But once you've diagonalized it, you can think of this as A times A times A times A times A. Each one of those could be written as MD M inverse. And if you multiply all these together, what pairs are going to cancel out right away? You got M times D times M inverse times M times D times M inverse and so on. What's going to cancel out? Yeah, anytime you've got M inverse and M directly multiplied together, they cancel out. M inverse times M is the identity matrix. M inverse times M is the identity matrix. The first one and the last one are still there because they're not directly multiplied by each other. There's all these D's in the way. But all that's left is D times D times D times D times D. That is D to the 5th, flanked by a single M on the left and a single M inverse on the right. And this might look like we haven't really simplified things because we still have a matrix raised to a large power. But for a purely diagonal matrix, it turns out that the result of that is just everything on the main diagonal to that power. Lambda 1 to the 5th, lambda 2 to the 5th, lambda 3 to the 5th. And raising individual numbers to the 5th power is easy. So to find A to the 5th power, and of course, diagonalizing it in itself is a big hassle. But once you've done that once, you can raise that matrix to any power you want really quickly. Write out the diagonalized form, raise everything in the main diagonal of that D matrix to whatever power you're dealing with. Left multiplied by M, right multiplied by M inverse, and you've got A to that power. In fact, it turns out this even works with non-whole number powers. If you want to find the square root of a matrix, Square root is the same as what power? Yeah. Since it's the second root, that would be a to the 1/2. And this same principle still applies. You can write this as m times d to the 1/2 times m inverse. That is m times, and then d is just the eigenvalues on the main diagonal. Zeros everywhere else. So we're just raising those diagonal entries, the eigenvalues, to the 1/2 power, which just means square root of all of them. And then zeros everywhere else, right, multiplied by m inverse. So multiply this out, and that'll tell you the square root of matrix A. That is some new matrix that, when multiplied by itself, gives you matrix A. And of course, this can run into complications if some of the eigenvalues are negative, which would give you imaginary numbers when you take the square root. But the algebra should still work out. So this is one of the many uses of diagonalization, which itself is one of the many uses of eigenvalues and eigenvectors. That diagonalizing a matrix, again, is pretty difficult or pretty tedious, but once you've done it, you can quickly raise that matrix to any power you want. Even non-whole number powers, even negative powers, any exponent. So that's a very useful technique if you're going to have to raise the same matrix to lots of different powers. This can save a lot of time. Any other questions on that? All right, that's all the time we have for today. Good luck on finals. Have a good summer, and I will see you later.